So, we've talked about Riemann sums, definite integrals. There's been a lot of algebra, possibly you needed to, step away, take some deep breaths. Please don't do the friends thing and put your computer into the freezer or anything like that. But I did promise there's a way to, sort of get around having to evaluate those Riemann sums, for which my students have throughout the years been pretty uniformly grateful. So what we're going to be talking about in section 5.4 references what we call the fundamental theorem of calculus, which has, I think, an appropriately, serious sounding name that kind of gets across how significant it is. So before we talk about what the fundamental theorem looks like, this theorem is going to be broken into two parts. So we're going to take a look at the first part here, and then that will get us to the second part, which lets us do the how do I evaluate definite integrals thing. So before we talk about that, you'll notice I've drawn a picture here of my nearly famous, generic mathematician curve. So I've got a graph of y equals f of t. That's not a mistake. You'll notice instead of having my horizontal axis be the x variable, x is like a tick mark on the horizontal axis. So I introduced what you might call a dummy variable, t. So what I wanted to take a look at is, as we've seen over the last couple of sections, this area that I've gated off between our two little goalposts here at a and x is a definite integral, right? So I could represent that like so. So we have the definite integral of f of t as t goes from a up to x dt. So nothing new yet. What we're going to do is define a new function of x using this definite integral. So I'm going to call that guy g of x. So again, this is now a well-defined function. The catch is we're defining it by integrating something else. So that's where a big part of this fundamental theorem of calculus stuff ends up driving. So we use this to get to the punchline that we're really after. So bear with me. So as it turns out, this feels like sort of a weird way to define functions, but yeah, it actually comes up fairly often in applications. So a couple of examples that I know of offhand. So physicists sometimes need something called the sine integral function that comes up in, I think, some applications involving optics. So it looks kind of like this. So we have SI of x, and it looks like the following. So it's not just a sine function, it's actually, that should not be sine of t over dt. My apologies. Sine of t over t, and we get the dt, but dt should never be in the bottom of a fraction, for our purposes. So technically, we have to sort of fill in a hole because this thing's not really continuous at 0, but the limit exists. We jumped through that hoop enough times now. Hopefully you're okay with that. So this is one example of a function defined by integrating something else. Another example, if you take a statistics course, a lot of statistical calculations are based on something known as the normal probability distribution, and it turns out a lot of that stuff ends up relying on finding areas underneath the graph of a particular function. So you might end up seeing an integral, i.e. area, that ends up looking something like this. So I'm cutting out some of the technicalities that make it work for a stats class, but you end up needing to evaluate a definite integral that looks kind of like that guy right there. So there's a couple of examples of this stuff in action. Now, where does this fundamental theorem thing come into this? So as it turns out, the first part of the fundamental theorem that we're going to talk about in this video is related expressly to functions that are defined by integrating another function. So the fundamental theorem of calculus, part 1. So I think our text uses just, the standard, numeral 1. If you wanted to use a Roman numeral, you could. So as it turns out, we don't really need to know a lot. You may be worried about that whole hypothesis conclusion thing. Don't stress too heavily about it here. So if we happen to know that the integrand, so I guess I should say, I could write that as f of t, but hopefully you get the idea. Changing the variable there is not that big a deal. But if we have a function and we know it's continuous from a to b, so then that function g of x that we've defined So as it turns out, this function defined by integrating f, so it turns out it's also continuous. That's good. Continuity has been important for a lot of stuff we do. It's also differentiable. We could take a derivative of this thing. We don't even know that about f, so that's kind of neat that we end up getting the ability to take a derivative for free. The punchline is what comes next. It turns out we can get an explicit formula for the derivative of this g of x function. All right, brace yourselves. You ready for this? I'm ready for this. That's it. The derivative of g is in fact f. That basically tells us, if you jump back to the beginning of the chapter, this is an antiderivative of the function f that we started with, because that means g has to be an antiderivative. So that's kind of where we end up getting to this definite integral evaluating thing. So this is super duper useful, because frequently you may want to find a rate of change somehow for something that was defined in terms of integrating something else. So now that we've got that formula in tow, we can go back to the examples that we saw earlier. So if you want a derivative of that sine integral function that we said physicists need sometimes, lo and behold, the fundamental theorem of calculus part 1 says, we can, like I said, if we plug the hole, we've got a continuous function inside the integral. So done. There's no other work to it. We don't need to use like a quotient rule or anything like that. We just grab our integrand, get rid of the integral trappings around it, and replace that t variable with x. Check. Don't try to do any more work than you don't have to. So similarly, I said we had this fella that the statisticians kind of end up needing sometimes. Remember, the ddx is just derivative notation. Hopefully that's that's okay with you. So if we take a derivative of this thing, again, exponential functions are about as well behaved as they're going to get. So the fundamental theorem lets us scrap that stuff, swap out the t for an x, done. So no extra monkey business required. So that's really nice. All right, I want to take a look at one more example before we leave the first part of the fundamental theorem alone, because it is in some sense like a derivative rule. Don't panic, we're not adding anything to your bestest friend sheet, but so let's take a look at a little more involved of an example. So I've got a couple of different things going on. One, we've got our limits of integration. They look a little bit different. My examples before have all used 0. I wanted to use pi basically just to get across the point that a value in the fundamental theorem doesn't matter. So long as continuity is a thing for you, you're good to go. All right, so our integrand on the inside is like cosine squared of t. There's two big issues we need to worry about at this stage. One, you might recall we've gotten awfully used to this. We need an exact match to the format that we have inside that fundamental theorem derivative formula. So first order of business, our variable's not in the right spot. That fundamental theorem formula had x sitting right here. We need to get that up there. That's not too tough, really, because we've seen those properties of integrals. If we flip-flop our limits of integration, that's right, all we need to do is slap a minus sign out in front of this fella. So, okay. So now we have pi down below, x cubed up top. Now, the fundamental theorem formula has just an x right here. That's not just an x, it's an x cubed, right? So, yeah, we still need to use derivative formulas. I'm going to need the chain rule in order to take a derivative of this thing. So we get to use the fundamental theorem, but we got to dig in and do a little legwork first. So the idea is I've got that minus that's going to come along for the ride. So the fundamental theorem says I can kind of cover up all that stuff. I just take this thing and feed it into my integrand. So I have negative cosine squared of x cubed But that wasn't just x. So remember, we've got an inside-outside thing going on. I need the chain rule. I need the derivative of what's sitting right there. Imagine replacing it with the u equals x cubed, if that helps. So then I need the derivative of that u. The derivative of x cubed. Our buddy the power rule jumps in and saves the day. I have this for you. The derivative is 3x squared. And I normally like writing the 3x squared out front. It's not the end of the world if you don't, but I remember making a mistake at one point where way back when I inadvertently assumed that I was supposed to multiply those two things together. You don't do that. So the chain rule and our definite integral, limit swapping property gives us what we need for the derivative of this thing. All right, so that's the first part of the fundamental theorem. You may be asking yourself at this stage, what does this have to do with working out definite integrals? We're going to get there. That's another video.